Thanks, Rosa, and Rafael for the introduction. In this quick lightning talk, sort of we're pitching why sort of workflow tools are ideally well suited, when it comes to sort of HPC and classical HPC computing, mixed with quantum. So to sort of kick things off, workload tools, sort of dealing with classical HPC and quantum computing, are sort of ideally well suited together. Given that today currently we're in the NIST era of quantum computers, where we have all the hardware vendors, we actually have limited number of physical qubits that are sort of typically a bit noisy. Developing efficient quantum algorithms for general purpose computing is sort of quite a challenge. In recent years, however, variational quantum algorithms, VAQs, have emerged as a promising alternative. They have shown a modest amount of success in machine learning and several optimization related tasks. And the premise of the whole VQAs is you have a classical optimizer that is being used to train a parameterized quantum circuit. So this straight away leads to heterogeneous computing, where the classical and quantum devices are sort of constantly in communication with each other, exchanging data and parameters back and forth. And so this sort of drives or puts quantum devices as accelerators, and augmenting classical HPCs rather than a replacement for them, right? So quantum devices sort of becoming more and more of a conventional accelerator, like GPUs, like tensor processing units that are widely available. So having said that, given the classical heterogeneous computing space already is quite heterogeneous today for users. A user may not have access to just a single on-prem cluster. They actually might have access to a consortium of clusters. Each cluster would have a different set of hardware resources, a different set of accelerators that users may have access to. And if a user has access to all of them, then sort of orchestrate having a tool that sort of abstracts away the heterogeneities and becomes all that much more important. And having said that, now HPC in the cloud is also becoming more and more relevant today. So not only that user may have access to multiple on-prem clusters, but having access to sort of cloud computing from different cloud providers also becoming increasingly relevant. And different cloud vendors have their own APIs for doing sort of HPC computing on their platforms. Now, with quantum becoming more and more relevant, it's just adding that much more to the heterogeneity. So quantum computers are sort of being used as accelerators in classical HPCs. And in this sort of simple example, where a user may be using a variational quantum algorithm to do some sort of machine learning, there's constant communication between the classical and quantum devices, and having a tool that sort of abstracts away this communication is sort of really important. And adding more to the heterogeneity further, like different quantum hardware vendors actually have their own sort of programming APIs and sort of the own interfaces that users would sort of have to learn in order to successfully execute code on those backends. So to sort of put things in perspective, like a workload orchestration tool that sort of aims to abstract away the heterogeneity that's being currently exposed to all the users. It's sort of, we at Agnostiq believe that it should be sort of very easy to adopt. So in the sense that the computing landscape is already so heterogeneous, the user is already having to, find a best set of hardware resources to get their workflows to run. The tool, if a workflow tool, should sort of facilitate that process, so it should have a shallow learning curve. Scheduling, in the sense that the tool should sort of provide an interface that's consistent, or sort of the user should be oblivious to the fact that whether a particular part of their workflow is sort of running either on-prem or on cloud. So the interface that's being exposed to the user sort of should be consistent across the environments. A strong aspect that workflow tools should sort of facilitate exchange of results, and should have a strong focus on reproducibility, in the sense that if workflows, users develop a workflow today, several months or years down the road, they should with some sort of confidence, they should be able to come back and re-execute that workflow and expect to actually have the same results returned. Visualization is also a good good to have. In the sense, if a tool is actually able to give you visual feedback of what the workflow is doing, exactly exactly which parts of the workflow are actually executing where and are in what state. Having that visual communication, improves adoption sort of that much more. And lastly, as I mentioned, like different quantum vendors actually have their own sort of program SDK, so on and so forth. Any tool that's aiming to orchestrate that whole thing should sort of be agnostic with the language that's actually being used by the users, so or it should be the tool should be able to easy to extend and have nice interfaces built in, so that interfacing with other languages becomes relatively easy. So why Python? In this case, Python, having looked at sort of the good feature set of requirements just now, Python is sort of a great candidate to actually have a workload tool written in. In terms of classical and quantum computing, especially with quantum machine learning and classical machine learning, most of them are sort of typically very data heavy. Python actually has great support for data processing at scale. Good examples of pandas is sort of the traditional example. Rapids AI and cuDF from NVIDIA. These are great tools that have shown significant speed ups in data processing and machine learning tasks. Unlike classical HPC, a lot of quantum SDKs and programming software is actually written more and more in Python, and they have high-level Python interface. PennyLane, Qiskit, Qtip, these are sort of good examples of quantum SDKs that are out there that are fully written in Python. And Python integrates well with traditional HPC languages. So it has great bindings with C and C++ that is still very relevant in classical HPCs. So to summarize, some of the challenges that a researcher may use and a workflow tool can aim to address is the reproducibility aspect, especially in quantum computing. It's still required that a lot of domain expertise ought to be needed in developing efficient quantum software. Having a low-level understanding of what the qubit topologies of the machine on which the software is being executed, how the noise is actually being propagated in terms of the circuit depth, so on and so forth. So all these things ought to be sort of taken into account when developing these workflow tools. And scheduling is actually a sort of a whole new area of in the sense that classical scheduling on the classical resources as well as on quantum resources sort of work on totally different timescales. Slurm, for instance, would actually work on the second level, but scheduling task on a quantum computer is actually being done on the microsecond. So bridging that gap in timescales is actually a big challenge, but it needs to be addressed. Having limited resources today on quantum hardware devices actually is a challenge. So there are long queues, and most of them are sort of being expensive. And programming each quantum device is sort of very vendor specific, and each vendor is sort of exposing their own APIs that the user ought to be learned. So abstracting away that heterogeneity is sort of also crucial, and it actually poses a big challenge. So with this, I would say, if this would be the end of the talk, but I'll be happy to take any questions in the subsequent discussions. Thank you.